Okay, this is Lab 3, Black Hole at Georgia Tech, Physics 2211, Summer 2024. So we've got the fundamentals we're going to be using in this experiment. The part 1 of this experiment is called mass of a black hole. So the goal here is to find the mass of this black hole right here, given that a star is orbiting it and that the only mass acting, or the only force acting on the star is the net force from the gravitational pull of the black hole. All right, so to get that answer, we're going to use Newton's law of universal gravitation as mentioned earlier, and eventually we're going to have to calculate the parallel and perpendicular components of the net force and the rate of change of momentum and use those in the end to calculate the mass of the black hole, which is given first by this equation and then down here in code. So the second part of this is don't crash. So the kind of situation here is that my alleged spaceship has landed on a planet which is nearer to the black hole than the star in the previous part. I take off from that planet's surface in the direction of the motion, which is the negative x direction, but the engines of my ship fail immediately afterwards. The gravitational forces of the planet and the black hole now govern the motion of my spaceship. However, before I took off, I planned for this. I calculated the initial velocity required to skim the orbit of the black hole and avoid collision with the planet at the rear of my spaceship. The graphic to the right represents the trajectory of my spaceship, which is in magenta, the orbit of the planet around the black hole, which is in cyan, and the black hole at the very center. It's small, but it's right here. So how did I avoid crashing? So to the right are the calculations which were needed to narrowly avoid the black hole and evade collision with the planet on the rear. So you'll see that we had to calculate the position of the black hole to the planet. We have to calculate the unit vector, and then eventually the force of the black hole on the planet. And then we had to do the same thing with the ship and the planet, and then the black hole to the ship, et cetera, et cetera. Then we have to get the planet velocity to actually make things move, the planet's position, the ship's velocity, the ship's position. And then after that, you kind of just have to mess around and try different velocities in order to get a situation like this one where you kind of narrowly avoid getting sucked into the black hole, but also escape the system. So what does this all mean? The question we're going to be addressing here is how are the parallel and perpendicular components of the net force from the parallel, or how are the parallel and perpendicular components of the net force different from the parallel and perpendicular components of the rate of change of momentum? Net force and rate of change of momentum are equivalent, but not the same. Rate of change depends on time, where force does not. Moreover, rate of change can be observed, but without knowing the mass of the black hole, it's impossible to find the net force. So let's say you're looking at the orbit of the planet or the orbit of the star, etc. You can see, and you can take a stopwatch, whatever, and calculate how quickly it's moving with respect to time, or how fast or how much time it takes to move around the black hole, but you can't calculate force without knowing the mass of the objects. So what if I desired to enter the orbit of the black hole with my spaceship that I discussed in part 2? So again, you just have to try out a few different velocities, but in the end, this is what I ended up getting, and this is the projected trajectory which went along with this. And this is the same mass that we're using all the way that we found all the way in part 1, and we use that as well in part 2. All of these are done on this in the span of a day, so we have to do a time reference, which would just be 60 times 60 times 24. Yeah, that'll be it. Lab 3, black hole.